Hello and welcome to another session in physics. In this session, we will be looking at the topic matter, atomic structure, states of matter, diffusion, osmosis, and Brownian motion. But before that, let us review the previous lesson. Welcome back. What is matter? Well, matter is defined as anything that has mass and occupies space. Sometimes too we say matter is anything that has weight and occupies space. Of course, at this point in our previous lessons, I'm sure you must have seen the differences between mass and weight. For the sake of this topic, mass and weight can be used interchangeably. Well, there is no single substance on earth that is not made up of matter. As a human, you're made up of matter. Your hand, your legs, your intestines inside you, your head, every part of your body is matter to you. The clothes you put on is made up of matter as well. But matter does exist in three different states, namely solid, liquid, and gas. So if something is not in the solid form, it is in the liquid form. And if it's not in the liquid form, then it is in the gaseous form. And already we've said that liquid and gases are classified as what we call fluids. Alright, so we're going to expatiate on these states of matter one after the other. Well, when we talk about solids, we have examples of things such as ice, like ice block. We have brick, we have metals, concrete, wood, etc. Examples of liquid are things like water, we have milk, we have oil. They are all liquids. While when we talk of gases, we talk about elements such as oxygen, nitrogen, carbon dioxide, and so on and so forth. These are all gases. From the diagrammatical representation here on the screen, you would see solids, their states, and liquids, what they look like, gases as well. We even have plasmas too. Alright, before we start expatiating on solids, liquid, and gases, let's talk about the structure of matter. You see, every single particle of matter on the surface of this earth has what we call an element, an atom rather. An atom is the smallest indivisible particle of an element which can have a separate existence. Imagine that this is a tuber of yam and you keep cutting this yam into pieces, you cut, and then you get the smallest particle of this yam and you cut it and cut and cut. You keep cutting until you get to a point where you cannot cut this piece of yam further. That part of the yam you can't cut any further is what we call the atom of that yam. Now, as you can see from the structure of an atom here, you would notice that an atom is made up of what we call a nucleus, and it has a revolving electron around an orbit or shell. In the structure of an atom, we have not just the nucleus, which is the center of the atom, but we also have protons, which are positively charged particles, and we have electrons at the outer shell, which are negatively charged particles. And of course, the neutrons possess no charges. They are neutral. Alright, so like I said, if we want to achieve what we call electrical neutrality, if we want to achieve that, it means that we have to find a way to make the number of protons equal to the number of electrons. So when the number of protons is equal to the number of electrons, we say that that particular atom is electrically neutral. Alright, now let's talk about molecules. Remember, we said an atom is the smallest indivisible particle of an element which can have a separate existence. Now, when we combine two or more atoms together in definitive proportions, we get what we call a molecule. So a molecule is a group of atoms of the same or different elements joined together in definitive proportions. For instance, from the illustration here, two atoms of oxygen will give us an oxide. And then when we have three of them, O plus O plus O, like three atoms of oxygen, doesn't give us an oxide anymore. It gives us what we call ozone. And it makes up the ozone layer which we have in the atmosphere. It is the depreciation of this ozone layer that has resulted in global warming and extremely high temperatures on Earth today. Now let's talk about Brownian motion. And you may wonder, what does Brownian motion have to do with atoms and molecules? Now, Brownian motions actually help to prove two important facts. Brownian motion proves that molecules do exist. Molecules exist. That is one thing that Brownian motion teaches us. Brownian motion also teaches us that molecules are continually in motion. Molecules are continually in motion. So what does that mean when we say molecules exist? It simply means that, for instance, when you're sweeping your house, you see dust particles moving and hovering in the atmosphere. Those particles you see are actually proof of the fact that molecules do exist. And when those particles come together, they form that particular dust. The same has to do with smoke. You see particles of smoke hovering up high above in the atmosphere. One single particle does not make up a smoke, but when particles of smoke come together, they form that which we know as smoke as well. When we're talking about different kinds of motion, we talked about random motion, and we said an example of random motion is Brownian motion. Now, Brownian motion, as you can see from the diagram here, is a motion of particles, molecules moving about randomly in their containers. It is actually proof of the fact that molecules do exist, and they are almost always in constant motion. Now, let's come to the real gist, which is the molecular theory of matter. The molecular theory of matter. Let's expand a little on the structure of solids. Now, look at this diagram here. You'd notice that this is a solid. Look at the way the particles, the atoms that make it up, are closely knit together. They are tight. They are staying very close to each other. There is no gap at all. And that is exactly what distinguishes solids from liquids and gases. Solids consist of molecules that are held tightly together. Tight is the keyword. They are held tightly together by what we call intermolecular forces. Now, these intermolecular forces are forces of attractions that help to hold molecules of an element together. Now, when these molecules are held in place by intermolecular forces, it makes these molecules vibrate about their mean positions. These molecules are stagnant in their positions, and this helps to give the solids what we call definite shape. The vibrations of these particles about their mean position or their point of rest helps to give the solid the definite shape. That is why your desk can stand. That is why your bed can stay at a spot, because it is made up of molecules held together by forces that prevent them from moving far away from each other. What about liquids? As the name implies, liquids are not the same as solids. But the molecules of a liquid are able to move about. They are able to move about within the given volume of a container. Liquids exist in a container, and for that reason, they are only confined inside that container. Liquids have no shape. They don't have any shape of theirs at all, but they assume the shape of the container. It is the container that gives them shape. So if you pour a liquid inside a cone or a cylinder, it's going to assume the shape of a cone or cylinder. If you pour it into a cube, it's going to assume the shape of a cube. There is one thing that happens when liquids are heated. When liquids are heated, they undergo what we call evaporation. They turn into the gaseous state because these molecules gain enough kinetic energy that helps them to move faster until they are eventually able to escape from the surface of the container. At this point, let's talk about gases. Gases are the weakest. Look at their molecular structure. They are very, very weak. Now, look at that of liquids. You see, they are a little bit closer, held together by weaker intermolecular forces. And then solids have the strongest intermolecular forces holding them together. But for gases, the intermolecular forces are so weak. They are so weak. So weak that they are comparatively far apart from each other when you compare them with the molecular forces binding the molecules of liquids and solids together. One thing about gases is that they move at a very high speed. They move at high speed. Because they move at high speed, they have the exact what we call pressure. Because of the velocity they possess, they exert what we call pressure. They exert this pressure on the walls of the container in which they are. And that is why they can explode easily. They can explode easily. This pressure causes them to collide with the walls of the container. So you have to be very careful when you're dealing with gases. You have to be very careful when you're dealing with gases. At this point, let's talk about diffusion and osmosis. When we talk about diffusion, we are simply referring to the movement of molecules from regions of higher concentration to regions of lower concentration as a result of the kinetic nature of their molecules. Yes, from the diagram here you can see two movements from regions of higher concentration to regions of lower concentration. On the other hand, osmosis is the opposite of diffusion. The only thing is that osmosis deals mainly with solvents, deals mainly with liquids. So in biological systems, the solvent we talk about typically is water. But osmosis basically is the movement, this time around, from a higher region of concentration of a solute to a lower concentration of solvent. Osmosis can also occur in what we call supercritical liquids. It can even occur in gases as well. The point is that it takes place through a device we call a semi-permeable membrane. There are a lot of factors that affect diffusion. There are about 5 of them. The first is density, the second is mass, the third is temperature, pressure, and of course the concentration or the makeup of that particular particle. Graham was one man that made a lot of postulations when it comes to diffusion, and he created what is being known today as Graham's law of diffusion. Graham's law of diffusion states that at constant temperature, gases diffuse at rates that are inversely proportional to the square root of their vapor densities. What exactly was Graham talking about? Graham was saying that we're going to have something like this, R inversely proportional to the root of m. We'll tell you what it means, and then it's going to give birth to something like this, where we have this inverse proportionality turns to k over root m. The constant there is k. Graham was postulating that we'll have r1 root m1, and then we'll have r2 root m2, where R simply refers to the rate of diffusion. R is the rate of diffusion. And then we have M. M is our relative molecular mass. Relative molecular mass. Remember that the rate of diffusion is given by volume. Of course, the volume of the gas divided by the time. That's the rate of diffusion. Alright, so that's what he was trying to help us understand. M is the relative the rate of the molecular mass, and R is the rate of diffusion given by the volume of the gas over the time taken for this. Note too that the relative molecular mass is 2 of its vapor density. And that's it for this lesson. Thank you for joining us in this lesson. To refresh memory on what we've just discussed, please take the test that will appear on your screen.